Go ahead.
So hello from me as well. I am Tiina Liimets and I'm a postdoc in Astronomical Institute, Czech Academy of Sciences. And I'm going to present today the project that I have been involved in the last few years, the follow-up of extended shells around B-bracket E stars. And my main collaborators are here listed on the slide. So B-bracket E stars are massive B-type emission line stars. They have intense Palmer emission. Low ionized metals are also visible in the spectra, and also numerous forbidden lines. They can be found in various evolutionary stages, from pre-main sequence to post-main sequence. They have strong infrared access due to the hot circumstellar structures, which are in a ring or disc-like shapes. They have been studied, if I may say so, quite extensively, although they have not been directly imaged, but through the radial velocities and aperture synthesis, they can reconstruct the images, and one example is here also provided. But somewhat neglected have been the large-scale shell of B-bracket E stars. And one of the pioneering works was published by Marston and McCullen, 2008, where they published their H-alpha survey of 25 northern sky targets. And they found that about 50% of the targets are showing nebular extended features. And they found that they are in various shapes, spherical, spiral-like features, ring-type, bipolar, or unipolar lows. But the reason for the mass loss is still not completely understood. Is it a steady mass loss over the whole evolution, or clearly some eruptive events have to be present as well? And because there are so many various shapes, probably the physical process is not unique, but there has to be several reasons. And this is the reason also because it's not fully understood why we started our project. We had two main reasons. First, to investigate further the already detected nebula, and we were very kindly provided by the previous survey the images that they took 20 years ago. So we have taken new images, and we will try to find if we can see any expansion in the plane of the sky with the 20 years, or maybe morphological changes of these extended nebulae. For the selected targets which are bright enough, we are obtaining kinematical information, so we could see a full 3D view, and as well from the spectra it's possible to find the physical parameters of the nebulae. And secondly, we wanted to extend the list in the north as well as in the southern sky, so that we could get a meaningful, statistically meaningful sample. So currently, our H-alpha imaging survey is done. We have mostly used 1.54 meter Danish telescope in Chile, but as well the Nordic Optical Telescope at La Palma and few other telescopes, depending on the characteristics of the nebulae. The follow-up images, when we needed to see further details or have deeper images, were obtained with the Gemini South telescope. Spectral observations were obtained using also the Nordic Optical Telescope and the ALPHOS with these long slit possibilities, as well as 6 meter Russian telescope, which has a scanning Febvre-Barot interferometer. Complementary radio observations we obtained with APEX to investigate the surrounding cold molecular gas, because our other observations in the optical range are mapping the ionized gas. And as I mentioned, we have finished the H-alpha imaging survey. We have added 32 targets. Out of those, 23 are in the south and 9 are in the north. And just as the previous survey by Marston and McCullen, we see that 50% of the targets have nebulae or nebular features. We have published 3 papers and few more are on the way. And here then few highlights. One of our most favorite target, the B-bracket E supergiant MWC 137. It has a sub-arc second disk, CO disk, which is very small. It cannot be seen in this image. It has an arc-minute ionized nebula, which here on the image is pink and bluish in the upper part. We did not see expansion in the plane of the sky within the 18 years of time duration. It's okay, we have to wait a few more years, maybe a few more decades. It has arc-minute warm dust nebula as well, which is here with red. It has fast amount of molecular gas, which is spread out several times to a larger scales than the optical nebula. The radial velocities along the optical nebula are varying a lot, and here I present these Febvre-Perot interferometer results in sulfur line, a sulfur forbidden emission line. They show that even though the radial velocities vary a lot along the slit, because we also had slit observations on different angles, position angles, but we see that predominantly the northern part is blue shifted, while the southern part is red shifted, and the radial velocities are from plus minus 40 kilometers per second. And also nebular densities are varying along the slits, and they are about from 0 to 800 particles per cubic centimeters, being more dense in the central areas as well as in the higher brighter emission line areas. Another interesting target is MWC 819, which is either an unclassified Breguet star or possibly protoplanetary nebula. In the first survey, it was identified as a unipolar lobe. On this side, I hope you can see my mouse. Our newer image with the GMOS, which is much more deeper and detailed, this unipolar lobe became actually, at least to me, it seems to be actually a background nebula on itself, because the little central star or faint central star emerged. With the black circles here, we note the already known features. Maybe they were not identified in the first survey because they were too faint, but now in our deeper image, we clearly see that these are nebular features, so they have been there before, but in red circles, we show the new features. And most intriguing is the one on the right, because that's perpendicular to the nebular feature, referring to be a jet feature possibly. And other B Breguet stars have shown jet features. MWC 314, B Breguet supergiant, but also mostly known as LBV. I myself am new in the massive star field, but I've learned that it is quite famous. LBV, and it's one of the brightest stars in the galaxy. It has a huge bipolar nebula. In the sky, this image is 18 by 9 by 10 arc minutes. Distance is 3 kiloparsecs, and that makes the physical size of the nebula 13.5 parsecs. Again, we were hoping to detect expansion in the plane of the sky, which we could not see because velocities are small, relatively small. However, when we obtained our deeper image, this one that you can see here, I started to wonder that the northeast lobe might be that the second lobe, the northeast lobe, is clearly part of the nebula, but before the lobe, which is in the west, was considered as a second, the second lobe. But here on this image, a northwest lobe has emerged. And considering that the proper motion of the central star is in the direction here with the white arrow, then it could very well be that the northwest lobe is the actual second lobe of this nebula. And this would make it strikingly similar to the cheeky purr, which was mentioned here on Monday, when Jason was looking for a planetary nebula and the stars which have planetary nebula and nova. and the cheeky bird is one of them, as Albert pointed out. And this, the planetary nebula of the cheeky bird has also this swept back nature, which is caused by the
2 minutes left.
Thank you. Which is caused by the central star, the dropper motion of the central star to the interstellar medium. So it could very well be that the second lobe of MWC 314 is actually here in the northwest. What is then the west lobe remains to be seen. But in order to confirm whether the northwest lobe is the actually second lobe, we obtained also radial velocities with the scanning Febvre-Perot interferometer. We made 4 pointings. Unfortunately, in the pointing where we wanted to see the information about the northwest lobe, the signal was too low due to some technical peculiarities of the observations. So we only got the kinematical information of the northeast and the west side, which shows that the northern parts of the lobes are more blue shifted, while the southern sides are red shifted, so implying a tilt in the plane of the sky. But we need to obtain further observations to get also the kinematics of the northwest lobe. And here to conclude, we added 32 P-bracket stars to the already observed 25. 23 of them are in the south, 9 in the north, and 50% of them show nebular features. We did not detect yet any expansion in the plane of the sky of 2 selected targets. We have obtained kinematical information of the nebulae. Some data is yet to be obtained, and we have discovered new features around NWC 819. And here I will leave you the slide of a little outlook for the future, because if we obtain additional observations on different wavelengths and do more detailed analysis, then we could disentangle the general question that what are the driving mechanisms of the mass loss that creates such a diverse shapes of nebulosity. Thank you.
Thank you. So I see that we have a question from Bruce. Please go ahead.
This is a great talk. Would you mind going back to your second slide?
Second slide, yes.
That one. Oh, sorry. Two forward. I forgot which one.
This one.
That one, yeah.
Okay.
So NWC 314. I guess my question's about that one. The nebulosity, the brightest nebulosity, has an S shape, right? So to what do you attribute that?
Well, remembering yesterday, the jets were making S shapes, but this is huge. Rotation of the central star. If there is a steady mass ejection and you rotate at the same time.
Maybe I can add a little bit to that, Tiina. This object is known to have a contact binary in the center. So this may certainly help to drive jets or mass ejections, bipolar or multipolar lobes.
Thanks, Mihaela. Mihaela is my supervisor here.
Okay, so we do have a question or a remark by Joel or so. It's also in Slack, please.
Yeah, that's right. Yeah, Tiina, the beautiful results, and thank you so much for this talk.
Not detected.
I just wanted to call your attention to this paper. I had to run back to the ADS and remember what the heck we had said, because we published it a dozen years ago now almost. But we looked at a whole bunch of supergiant B-bracket stars in the Large Magellanic Cloud with Spitzer IRS, and found signatures in their mid-infrared spectra that were almost exactly like what you see around protoplanetary disks or from protoplanetary disks orbiting Herbig AE/BE stars. So these are essentially, mega protoplanetary disks orbiting these stars, and we found some large-scale structures like you see here in the Spitzer images. So it's very gratifying to see these same structures popping up in the galactic population of B bracket E stars. And I guess my question is, have you looked carefully at the mid-infrared signatures or whatever you can tease out, from the available photometry and so on to see if you can see evidence of long-lived orbiting disks in these systems?
But by the disks, you mean the sub-arcsecond disks, which are very, or you mean the larger scale structure?
No, I do mean the smaller scale structure that is so difficult to resolve. Yeah.
Yeah, I am mostly involved to investigate the large scale structure. So maybe Mihaela can comment again
Sure.
about the smaller disks.
Well, for the galactic stars, well, we have not looked into detail yet in the infrared. In what we know about the disks of these galactic supergiants is that they are all pretty much structured. So there was a nice work by Grigoris Maravelias in 2018 investigating the circumstellar atomic and molecular gas and showing that all the stars are surrounded by multiple rings, but each star has its own sample of rings or arcs or spiral structures or arcs or bows. So each star is very individual, and at the moment I find it very difficult to find a common mechanism that is producing such a diversity.
Yeah, one more quick comment then. I think these objects are sort of the high mass, I wrote in the Slack, these are the high mass extension, I think, of the post-AGB star class that seem to have circumbinary disks, binary companions and circumbinary disks. So it'd be really cool, I think, to stare at some of these with something like Sphere, to try to look for orbiting disks, essentially. I think they should be there.
Yeah, I fully agree with you. I also think that they should be there. We are now trying to use interferometry for those stars that are close enough, but as you know, the resolution and these structures are so small that it's very hard to resolve them.
Sure, yeah. Well, at least you have a chance with these galactic stars. With the LMC stars, we gave up at a certain point.
Yes.
Thanks so much. Yeah.
Okay, so now we have a short pause. So just grab a cup of coffee or a piece of chocolate or whatever you want, and let's reconvene at 15 depends on where you are. It's 15:46 now, and let's reconvene at 55. So in 8 minutes. Martin, you want to say something?
Yes, maybe Laurent could try his talk.
Yes. That's what we plan to do during the